answer your question? Yeah, it's a little bit confusing with respect to how we did it.
C was omitted because it was already
Updated into GJ, correct, yeah, and we put in the open list, so now the label contains C, exactly. Yep. There was another question? Yeah.
One thing, there was something like in the extra we are over approximating in the extra we are under.
Say again, the extra operator?
We were over approximating some particular label was given.
Right.
Yeah, that particular context was interesting.
Right, so if the costs are positive, the labels we have, the GI for any node I, is always greater than or equal to the distance from start to I. So that's guaranteed throughout the whole algorithm.
Is it like a Euclidean distance?
No, the true, you mean the true distance?
Yeah.
Not necessarily. It's the shortest distance according to our graph from start to I. It doesn't have to be Euclidean, whatever our problem is. Distance from S to I is the shortest cost or the lowest cost of going from S to I. So the algorithm guarantees that over time the label is always greater than or equal. So initially we start at infinity. The moment we discover some path, it falls to some finite value, but it's still larger. Over time, while it's in open, it goes down, 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 down. The moment you remove it from open, it becomes equal. Yes?
I have a question regarding the Voronoi diagram. We have the Voronoi diagram as the edges are the places where we are equidistant from obstacles, or we can say we are farthest away from the obstacle.
Exactly.
But is it like, and we discussed that this is not optimum because we could be on a suboptimal path.
Yeah, in terms of, we're sacrificing distance here for safety in a way, yeah.
But if we know that if we need a particular safety margin, can't we just use a reduced visibility graph with like padding?
Yeah, we can, great question, right,
So
yeah.
why do we consider these, like the trapezoidal decomposition of this?
We don't have to. I guess the most widely used algorithms in practice, which we'll discuss mainly, are derivatives of A star, which is what we're doing now. And exactly like you said, we haven't mentioned this yet. But one way to introduce some safety from the obstacles is to inflate your map, for example, with the radius of the robot or even more. Or you can use some cost in your map, which says if you're really close to an obstacle, it's not very desired. So you can have some function which transitions from 0 in free space to, let's say, 100 or 1000 in an occupied space or infinity, and in between there's some smooth transition which roughly tells you how comfortable are you with getting so close. So that's one way. The second very widely used way is this random probabilistic graphs, in which, again, you can kind of choose to not add edges which get very close to the nodes. So yes, you're right, you don't have to necessarily do this maximum clearance construction. Yeah, it's actually rarely done in practice, but it's good to know that it exists. Yeah. Okay, any more? Yes?
Bro.
Yeah.
Yeah, it's
It's smaller than GTAW, yes. Yeah, I think that was his question exactly. So the answer is that GI, I guess here was already updated in the previous iteration when we were putting the node into the open list. So we already did the label correction, and then now we're removing it. So CIJ is included in GI in a way. Okay, let me try to explain again. But yeah, it's what I answered to Chunlin a couple of minutes ago. Let's see. So let's only, yeah, let me try one more time. Okay, so let's only look at Dijkstra first, forget about the heuristic. So in Dijkstra, we're removing nodes from the open list in the order of G values. So whatever has the smallest G value, that's what we remove. So if we assume that, then we can actually do the second condition in a different way. So instead of enforcing it here, I can remove the condition and instead terminate when tau has the smallest gi in open. Why is that? Because essentially now we're not checking this condition, but we know that we're removing the nodes in the order of their g value, and if we remove the goal, we can stop. So essentially every node we have removed from the open list is gonna have gi plus cij smaller g tau, because we remove the nodes in the order of g. If we remove g tau earlier, we will terminate. So instead of checking the condition, if we remove in this way, it's kind of equivalent. And then in A star, we are just adding plus h when we remove.
So that one is AGI plus CIJ.
Correct, yes. Because if it wasn't, we would remove g tau first, and we would terminate the algorithm. Does that make sense? If gi plus cij was larger than g tau would come out of the open list earlier, because we're removing nodes in the order of their smallest g. So if g tau has a smaller g, it will come out first. So this node will never be expanded. Does that make sense? Yes, which we set right here. Right, if I remove that question, I'm immediately going to get gj is gi plus cij. Yes. Yeah, because instead of checking the condition now, we directly put the node in the open list. We correct the label, put it in the open list, and then we check the condition when we're removing from the open list, instead of checking it over there. Does this make sense? Exactly. Yeah, it's not very obvious. I didn't clarify this point very clearly. Yeah, if it bothers people, I can try to show this more clearly. Yeah, I kind of showed you what the algorithm. Yes, so you need to be using priority queue for this to make sense. If we're using some other data structure for the open list, we're not enforcing that. Yeah. Okay, I'll think about how to clarify this by the next time. Yeah. More questions? Dallas?
Okay, so in terms of PR1,
Yeah.
you said that something that would help us understand how to approach the task is do the 2x2 grid first.
Exactly.
And then you said like everything would make sense.
Correct.
So I tried to work through that problem by hand, but I was still getting a little bit confused on.
By hand would be hard, but yes, you can try.
Okay,
I was
okay.
thinking implement dynamic programming, but
So I mean, the example I was going off of was the one you showed us, where you created like a network kind of where you could possibly be and like how you go in, because like that's the easiest for me to understand. Dynamic programming is like calculate all your goal states and then work your way backwards and find the minimum cost. It makes sense in the context of a grid environment too, because you can start at the goal, and then like if you're thinking of a 2x2 grid surrounded by walls, like you could have come from infinity, but that doesn't make sense, which would be like a wall. You come from another infinity, or you came from 1 and 1.
yeah, let's try it.
Okay, yeah. I was wondering, can we do it together from scratch? 'Cause,
Yeah,
like,
let's give it a shot.
okay, thank you.
Okay, so let's say we have this environment. Let's label these nodes 1, 2, 3, 4, and then let's say our goal can be in one of two places. That's kind of like part B. I don't know where exactly the goal is. So the goal can be here in 2, or the goal could be here in 4.
Mm-hmm.
Okay, so before we do any algorithms, we need to define our state space, control space, motion model, cost, and so on. So let's try to do that first. So what is our state space?
The XY direction, and since there's no key in the widgets.
Yeah, no key, no door, right?
So it would be,
So XY is position. Okay, so I'm gonna kind of simplify things. So I have a position which has possible values 1, 2, 3, or 4. Okay, that's one of my state variables.
but there's also wall, so you.
I'm gonna ignore the walls. I don't need to know where they are. I'm just, with my motion model, I'm not go, or with my cost function, I'm not gonna allow leaving. So yes, you can think that they're walls, but they don't need to be part of your state. What else do we need in our state? Is that enough?
4 directions you can face.
So those are, oh yeah, orientation. Let's simplify those also. I'm gonna change the actions a little, but yes, in your problem you'll have to do that, but I wanna make the problem a little simpler here, because we'll be computing by hand. Let's make our actions be up, down, left, well, I'm just gonna use first letter. Yes, let's make our actions be up, down, left, or right. So we don't have to worry about, there's no orientation, just gonna move left, right, up, or down. Just to simplify a little, yes, if you have orientation, you should make it part of the state. What else? Do we need any more? So this is our action space. Do we need anything else? We would need a cost and the motion model, yeah, but before that, we didn't handle the fact that the goal could be in one of two places. Say again.
Like whether that was in
The goal is in 2 or 4, yes. So let's introduce one more variable, which is 2 or 4, of where the goal is, okay? So then our state is what? Let's call it x is pg. And what is so the state space, x is this. And the size of the state space is? How many states are there?
Be 4 times 2 times.
8, that's right. Okay, good. Does this make sense so far? Okay, now let's talk about, yes.
Why goal is in the state space?
Because we don't know where it is. It can be either in 2 or in 4, and we're not sure. That's like part B.
Oh, so string markings.
Well, part B inspired, yeah. Yeah.
There's a quick question. It's related. So, like you said, so here goal is part of the state because this is like part B where we don't know where it is.
Correct. We're going to get one of those 2 environments. The goal is either in 2 or in 4, but we don't know which.
In part A, our control policy can just be like we're given the position of everything in the environment.
Correct.
ahead
In
of
part
time.
A, you don't need to do that. Yes.
Okay.
Yes. We are doing sort of part B inspired example. Yeah.
Okay,
Yeah.
thank you.
Okay. Good. Yes. So let's try motion model then. So we said our motion model is a function f, which takes what? What are the inputs? What are the outputs? X has to be an input. And u. Okay. So how do we implement this function? So
Which is different x, different state.
yeah, I mean, if I'm implementing in Python, I would probably do slightly different description. Yeah, two ways. One is we can do something like if u equals up, right? Then yeah, we can implement it in a very brute force way, right? So if u is up and x is 3, then x equals 1. If u is up and x is 1, then x equals 1. So I'm not going to allow leaving the environment. If u is up and x is 2, then x prime, I guess, let's call it prime, is 2. If u is up and x is 4, then x prime is 2. Does this make sense? For the up motion, and I would have to add conditions for down, left, and right to compute the motion model. Maybe a slightly cleaner way of implementing this. Let's show another way. But yeah, before I erase, does this make sense for a motion model? We need a bunch more conditions for the other actions.
So why don't we just put the position as x, y? It would be easier for us.
Right, yeah, I was gonna do that. Let's do that so it's easier to, yes, so let's change the position a little bit to be, let's relabel things. Yeah, that would be easier. Let's call it 0, 0, 1, 0, 0, 1, and 1, 1. Okay, these are our possible positions. So we can implement this function a little simpler. Okay, let's revise our design a little. So the goal is in either 1, 1 or 1, 0. And then let's change our control space a little. So our control space is, let's see, was up. One second. Wait, this is right actually. Yeah, but our control space. Yeah, one, -1, 0, 1, and 0, -1. Okay. Yeah, with these definitions, it's a little bit easier to write the motion model. Okay, now it's very easy. Let's revise a little. So our motion model is f of xu is just x prime is x plus u, and then if x yeah, we'll have to check the values, right? If x, let's say this is the first element, is less than 0, or x prime 0 is greater than 1, or x prime 1 is less than 0, or x prime 1 is greater than 1, then x prime equals x. Okay, this is our motion model. Does this make sense? So the second part doesn't allow us to leave the environment. The first part just moves us left, right, up, or down. Okay, then cost function. We need what? Stage cost, and wait, we don't need stage cost. What problem are we defining? Shortest path or optimal control? That's a good question, actually. So I'm sort of like defining an optimal control problem,
Yeah.
right? We said they are equivalent. So what should be the planning horizon? What was the planning horizon? Remember equivalence between shortest path and optimal control? How do we pick the planning horizon? Yes, and we say how many states are there? 8, so this should be 7, okay. Or, in fact, anything larger is fine, but we need to terminate our algorithm early. How do we terminate early? We go back to, I'll show you later, but we go back to this lecture where we did the forward dynamic programming. We have the termination criterion to stop early. Okay, we also need stage cost. So stage cost is, we can just make it 1. So any action is cost 1, and we need terminal cost. What should that be? Under certain conditions, right? How?
So if we're at the go state, it's 0. If we are at
Any
state
other
other than
state?
those states,
Exactly,
it's
exactly.
infinity.
Right, exactly. So let's define it this way. So our terminal cost is of PG, right, is 0 if G, wait a second. No. Is 0, let me need more space here. So terminal cost of PG is 0 if P equals G and infinity otherwise, right? So if I'm not at the goal, I lost the game, so pay cost infinity. If I'm at the goal, cost is 0. Does this make sense? Yes?
Our stage cost can also be 0 if we reach the goal.
Correct, yes, we need to enforce that. Yes, good point. Yeah, let's revise that. So I'll erase a little bit here the motion model, because I'm just going to leave this as the motion model. You got the extra conditions here. Yeah, let's fix that as well. So our stage cost of PGU is, let's see, 0 if Well, yeah, our motion model, we need to add one more condition. Remember, if we're at the goal and whatever action we execute, we stay at the goal, we should add that as well. So let's fix the little as well. So if, maybe in the beginning of the motion model here, let's fix a little. Okay, so if P equals G, right, then X prime equals X, else we can do X prime equals X plus U and then correct for bounds. And then we said for the stage cost, again we have 0 if P equals G and 1 otherwise. Yes, okay, good. Makes sense? Makes sense? All right, now, okay, now we defined everything. Dallas, is this helping?
Yeah.
Okay, so now we defined everything and now we can run the dynamic programming algorithm. Yeah, question?
In the stage cost, should it also be infinity if the U is not possible on stage X?
We allowed everything, I guess. Yeah, two ways of encoding that, good question. We can either put it here in the motion model where we don't allow it to leave the bounds, or we can leave the motion model be simple, so not put this, but then we'll have to have like infinity if outside of bounds. So either is fine, there will be equivalent. So you either need to put it here, like when you execute a control, you're not allowed to leave, or you can allow it, but then make the cost infinity.
We shouldn't allow it because like that will just keep on making infinite more states.
Say it again.
So if we are still like if we are
Right, yeah, you don't want to introduce new states as well, yes. But you can say something like yeah, you would still need to correct for the bounds. I agree, because you don't want to have an X which is not in our X set is only those 4 states, so we cannot have a state that's not there. True. Yes, so we will need to have this, and because of that, I don't think we need to add the infinite cost here, because we will never be able to exit, and we'll pay a cost of 1 for nothing, for staying in one place. So it'll never be optimal. You're right, if we allow to exit, we will have to have add more states, and then have a cost of infinity, which, yeah, completely fine to model this way, it just has more states, yeah. Okay, now how do we run the dynamic programming algorithm? What do we need to do?
Second step is find your terminal value function.
That's right, yeah, so how many states did we have? 8 states, so how do we represent the value function? It will be a vector with 8 entries, which will correspond to the values of the states, right? So I will initialize my value function at time t, which we say is 7, as a vector with 1, 2, 3, 4, 5, 6, 7, 8 entries, and they corresponded to position 0, 0, and goal at top left. I don't know how, or top right. So let's say scenario A, something like this. So this would be 1, 0 scenario A, 0, 1 scenario A, 1, 1 scenario A, 0, 0 scenario B, 1, 0 scenario B, 0, 1 scenario B, and 1, 1 scenario B. Whoops, this is hard to see here. How do I? There we go. Okay. Does this make sense? So these are our entries. So let's try to do that. So what are the values here? At time t, it's going to be equal to the terminal cost, right? So let's initialize that. What should be the values?
What is the goal position of scenario A?
Let's say it's the top right, the 1, 1. Yeah, I identified. Yes, let's say scenario A is G equals 1, 1. And scenario B is G equals, what was the second one, 1, 0 or something like that? 1, 0, yeah. Yes,
For our problem that we're given in part B, we're not given the goal location, the key location, or the door location. Are we given the wall locations?
you know the walls and the goal, key, and door locations, you don't know, but you know they're one of 3 possibilities or something like that. So they're kind of like this example where I have 2 options, where G is either 1, 1 or 1, 0.
Okay, so we are given the walls, we're just not given the variable states of the goals or.
Exactly, yep. Jason?
Going off that, but we are given the positions of the key and everything at, like, once we're given our initial state
Yes,
will include that.
once you're given the random map, once you're given one of those 36 maps, you can look up the goal and the key position right away, and you should. You can use the properties of the environment to check where the goal and the key is. So during, when you're running your algorithm, it's one of 3 options and you don't know which one it is. Once your algorithm is done, and you have your policy and you want to run this on a particular environment, you can look up exactly where the key and the door is because you have one of those environments.
So what you're saying is we have our probabilistic map or graph, right? And then we just, when we're given the map, we apply costs based on the map. Like
Yeah.
to where the walls are and things like that.
Exactly. Walls actually don't change, but yes, that's right.
Okay,
Correct.
perfect, thank you.
Yeah. The only variations are where the goal is in one of 3 places, where the key is in one of 3 places, and whether the doors are open or closed. I think these are the only variations. So your state space has to consider this, kind of like in this example, we introduced a variable G, which tells us whether the goal is top right or bottom right.
Okay.
Let's see, go for it.
So what I understood from this is, your overall state space will be a very big map, and whenever we look up the key position, we only, like, let's say there are 3 key positions, so, and imagine a very big tree. So it's like, when we know the key position, only that part of the tree will be executed in that manner.
Exactly, yes.
So do we know, like, when we enter the map, do we know, like, whether the door is open or not?
Yes, when you're given the map, you can look up that right away. You don't need to wait until you get to the door and observe. Yeah, we don't do partial observability for now, so yes, you can immediately see where the key is, where the goal is, where the doors are open or closed, yes.
Then at the same time, then we are basically, we have 36 different policies just tagged onto each other, and we call that one policy depending on what we know about the door. And
Well, you can think of it this way, but ideally we should have a single policy and this information should be included in the state space.
Right, so like, we are, in a way, we are kind of overloading the state,
Yes,
like, and it's the same thing, like, we could call it 36 different policies for each location and orientation.
maybe, yeah, almost like that, but the approach we should take is overload the state. Yeah, we're practicing how to define state space and how to define a single policy. We're not practicing how to solve 36 different problems and concatenate them. We want to think about how to define states and how to define a single policy which works in many scenarios. But yes, you're right, technically, sort of something like this is happening, yeah. Go ahead.
So this is also more of a conceptual question, but at the end of the dynamic programming, our control policy, at least in this case, would be like another 8 vector that would describe going from any like initial state to the goal position.
Exactly,
So,
exactly.
and then because of the principle of optimality, we know that each individual control input at that state is optimal.
Exactly, correct. So what will be our policy? That's a good question. Let's answer that. So what is the policy, right? It's gonna be a vector, but we also need what? We need time as well. So it's going to be 7 vectors of size 8,
Oh, okay.
right?
Yeah,
Because we're gonna have a policy at time 7, we'll have a policy at time 6, we'll have a policy at time 5, and we'll have a policy at time 4, policy at time 3, and so on. And each of those will be of size 8. Does this make sense?
Oh.
And if we're at time 1, we're going to be using the policy for time 1. If we're at time 2, we'll be using the policy for time 2. for time 3, we should be using the policy for time 3. So time matters as well.
Right, but like, I'm just also thinking about this like computing it backwards, but like, if you start from the goal position and compute backwards, a lot of these states aren't technically like reachable at say like time 1, right? Like if you're computing backwards.
Correct. Yes, but our policy will again give us an action for every state at every time. Yeah.
Okay.
Yeah, we'll answer this more precisely when we start doing the algorithm, which we'll do a little bit of
I
now.
think
Yeah.
what he's trying to say is at the end of the computation, we might find a matrix that contains the optimal control for every state.
Yeah, exactly. That's true. Which is the policy.
But we don't need the time. We just need
Well, we do. So in finite horizon problems, the optimal policy may be non-stationary, meaning it depends on time. So it might be that what you do at time 0 in this state can be different from what you do at time 5 in this exact same state.
Okay.
Because time matters as well. Yeah, because you have a terminal time. So here's the difference. Let's say I'm trying to get to the exit and I have 1 hour versus 5 minutes, and I'm trying to minimize. I want to go slowly. I don't want to exert myself. But if I have 1 hour left, I can go really slow. But if you have 5 minutes left, you would go a lot faster. So that's why you're right. Even though I'm starting same place, the time I have remaining also determines what I do. So that's why the policy, yes, it's a vector with 8 controls for one of each states, but it has to be we need to take time into account as well.
Okay, that makes sense.
So in our problem, it might actually not matter. You might see that policies are the same for the different time steps, but don't assume that. Compute them. Yeah.
Okay.
Yes.
Can you explain a little bit why the horizon is 7?
We discussed in lecture 4 that we can convert from a shortest path problem to an optimal control problem, and we said that because we had this assumption of no negative cycles, the longest path that could be optimal is the number of states minus 1, because you would visit every state once. It doesn't make sense to make cycles because the cost increases. No negative cycles. If you make a cycle, cost goes up. So the worst case scenario is visit every state. So that's why the number of time steps we need is number of states minus 1.
Because I was thinking
So in our case, we have 8 states minus 1 is
we
7.
can
Yeah.
we can find the optimal trajectory like less than 7 steps.
Correct, yes, we could find the optimal trajectory in less than 7 steps, and we can terminate early. So how did we terminate early? We can terminate our algorithm early. What was the condition? Does anyone remember? Yeah. You want to say what the condition is? Or- Is it second? The value doesn't change. So if we find Vt for every I is equal to V t minus 1 or t plus 1 for every I, then stop. So we can terminate if this is true. So if the value function and the previous and the current time step are exactly equal for every state, we can stop. So this can happen. I think we had an example in this lecture 4 where this happened early. So we had something like a graph we had 7 steps, but at step 5 they became equal, so we terminated. So here is the same. You can add this condition to the algorithm. If this happens, you can stop. Yeah, question?
Doesn't also have to not be infinity as well, like for this condition?
Say
Because
again?
doesn't it have to not be infinity, the value?
I think it's fine. As long as they're equal, it's okay. So it's possible that for some states, the value stays infinity forever. And that might be the optimal value.
But if this was like your break, to break out of the loop, and at time 1, or at your initial spot, you'd be infinity, and then the next one you're infinity, so you haven't reached back to your start position.
But it wouldn't be for all states, yeah.
Okay.
It wouldn't be for all states, yeah. If it has to be equal for all I, yeah, for all I, not just one, all I, yeah. So yes, you're right. Some states will be equal because they all have infinity, but there will be some that are not. So the moment they all become equal, that's when it's terminated. Yeah. Okay, so let's try the algorithm a bit. So tell me, how do we initialize the value function here? So what should be the values of v? Yeah.
It should be like infinity everywhere, but whatever the p is equal to,
Yeah, so which ones are zeros, right?
I think.
This is 0, and this is 0, and the rest are infinity.
Yeah.
Does this make sense as initialization?
Yeah.
Okay, great. So now we're on the way, right? So we can go on, we've computed the value function times 7, so we can go one step back. Okay, what do we do next? So now we make time equal to 6, and what do we do then?
You have to do your Q function.
Q function.
Yeah.
Right? So we have to do the Q function for every state and every U. And what was the value of the Q function?
The stage cost plus
Stage cost
V7.
Stage cost plus.
Plus V7 for all X and U.
plus value function at
At next state.
next state. How do we do this? Motion model. Next U. So how do I implement this in Python? I have a function f that I defined on the previous slide. I have a function L which I defined on the previous slide. So I call f plus V7 I computed. I call f and L and V7 and I compute Q. Does that make sense? And I have to do this for every X and every U, right? So this will be for all X and X and all U and U.
The goal is to return a singular value that corresponds to like an index of your value function array.
Say it again.
Like
Oh,
like f of x is going to return a number which is an index of like what you want to select from.
Correct. There will
Okay.
have to be some conversion because what our f returns currently was the state, which was something like 0, 0, and some position for the goal.
Mhm.
We need to convert this to, but there are 8 states, so we need to label them. So we need to have some way of converting between the state value to the state index. and
Okay.
back.
So it's going to return a state and then you say like from V select the state that it matched.
Correspond- Yeah,
Okay.
because every entry of V corresponds. So a very easy way of implementing this, instead of doing arrays which require indexing,
Mhm.
you can use dictionaries for everything,
Yeah.
and that makes it super easy.
Okay.
So if your value function is a dictionary, you can directly look up. You can
Yeah.
give it the state as the key.
Like which position corresponded.
Yeah.
Okay.
So yeah, just dictionary, no conversions are necessary.
Gotcha. Okay.
Yeah. Yeah. Question.
That's one concern I had. I was able to like do the 2x2 using dictionaries.
Nice.
For like the 8x8.
Yeah.
Is it like efficient enough? Because we have a lot of states for it.
Correct. Yeah. The problem will become quite large. Yes. I mean, efficient enough. What does that mean? You have until the deadline to compute. Yeah.
I think it does a lot, actually.
Hmm?
I think it does a lot.
Yeah. We chose the size to be challenging enough, but not impossible. Yeah. Yes, it's gonna be large, but yes, efficient enough to compute. Yes. Not shouldn't take more time than SWAM and 76A. So, you had another question? I'll come back to you. Yeah.
For the Q function here, since we have 8 states and 4 controls, then we need to run 32 shorties.
Yes, but it might be more efficient. So you can think about implementing your L and F functions such that it returns all possibilities at once. So you can pass in, so it's kind of broadcasting in Python. You can pass in your whole state space and your whole control space, and it can give you all possible next states. So you can do it with a single call. You don't have to use a for loop, but you can. You can have a for loop for every X and every U, which, as you said, will be 8 times 4 number of calls, or you can implement these functions so that it computes all next states for all states and all controls. Both are fine. Yeah, you pass in the list of all states, the list of all controls directly gives you all the next states. Maybe do the for loop version first. For the 2x2 example, for sure, do the for loop version first to understand how it works. Then you can optimize your algorithm to make it more efficient, and then try part A. That would be my suggestion of sequences. Yeah.
Let's not guess the question, but how do we have f x comma u? How do we input it into V7?
Yeah, that was a question that we discussed earlier. So you can use a dictionary for V7. That's the fastest, maybe not the most efficient, but the easiest way, because a dictionary allows you to directly give as a key something like 0010, right? If this is your P and G, if this is your X, I can call V7 of this. If this is a dictionary, I can do that. Does that make sense? So a dictionary allows the key to be tuple. So that would be the easiest. If you don't do this, you have to have you need some labeling. So you can go, this is well, I think a lot of you are in electrical engineering, right? You can go from a binary value to a decimal. So you can go binary to decimal conversion. I'm sure you've studied this in some class. So that would be a good way to convert. Yeah. Does this answer
Some point.
question or no?
I'll get that.
Okay. Back to your question, which
Yeah, I was still on the stage cost being just 0 and 1 and not infinity. So let's say like we still have like a pickup key. Like one of our U is to pickup key.
yes,
And
yes.
if we go over all the states and all U's, there will be some where there is no key and we still try to pick it up. That
You don't have to give this infinite cost. You could just give it a cost of 1 still.
yeah. So if I give that the cost of 1 and from V7, let's say it does not return infinity because the stage will not change. The state will not change it out. The state won't change, right?
Yeah, the state one. If there's no key or you execute pickup key, you pay cost 1. Your state doesn't change. Correct. Yeah.
Let's say it's not in at that state V7 or whatever VT plus 1 was is not infinity. So Q value there would be updated to something or not infinity. So like
Yes,
why-
sure. Yes, correct.
isn't that like
That's true.
That's-
Yeah, the
that's-
Q value will be updated to something that's not infinity. That's
that
fine.
should not happen, right? Because if
But if V7 was not infinity, it means there's some valid state there, right?
yeah, that state was valid, but going from a state that's not so that state X was valid, but like picking up key at that state is invalid.
Well, we said we allow it, but we pay a cost of 1. So it's still a
Oh,
valid action.
we allow it.
Yeah, yeah. I think you can allow picking up key anywhere, but you're not gonna have a key, I guess.
Oh, okay.
You can pick it up, cost you energy, but you don't get the key.
Oh,
So,
okay.
yes, it's allowed, but it's a bad action to do. So, yeah, you can allow it, but
What about,
the dynamic program is not gonna choose it.
What about like trying to go through a locked door without a key?
Then you should use infinite cost, yeah. Yeah, entering something that's not allowed, which would be wall or locked door, that should be infinite, yeah.
Like yeah, when talking about locked doors, I remember like in the last lecture you were saying we can include those in the states as well. If
Correct.
We can just not include those in the states, and just like if my stage cost at crossing a door, locked door without a key is infinity, that will just take care of it, and I don't have to like increase the number of states.
In part A, yes.
Even in part
B,
B.
no, because you don't know whether the door is locked or unlocked. And when you're running your dynamic programming, is before you know the environment. So you need to have cases for if locked, if unlocked. And if you do that, it's like having it in the state. Yeah.
Oh, okay. Okay, that makes sense. Okay.
More questions? Oh, for the other part, let's see if there are more project questions, and I'll come back to this one. Yeah.
I still didn't get it the part of using the dictionary instead.
Right, so instead of an array, you can use the dictionary data structure, right? So it's dictionary.
But why we cannot just use like ND?
It's not that bad.
Oh, you can use an array, but then you need to have somewhere converting a state like 0010, array state
Yeah.
numerical values from 0
Like,
I feel like it's not that bad. I'm just not approaching it right. You know?
0010.
like I was doing it completely wrong.
Number of 0 to 7.
Okay.
So you need some function which goes state to
I'll
index,
take your
index to state. If you use a dictionary, you can see that. If you don't use a dictionary, you need to label. So a very simple function is that 0, 0, 0 is 0, 0, 0, 1 is 1, right? But you need some function which labels.
I did good.
zero 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 is what is zero zero zero?
State.
It's crazy.
So,
Non-engineering.
the first one position, and this is the goal position.
Oh. Oh.
So we need to label the state somehow if we wanna store these value functions in array. We need to know which index corresponds to which state, right? Because your indices are from 0 to 7, which state is that, right? So we need some function which goes state to index of that.
Oh, we need to label them. We have.
If you're storing a value function in an array, you need to know which entry there corresponds to which state, right?
Yes, we can just use a 4 by 4 by 2 matrix.
Sure. Yes.
Which every entry is just the cost of.
Yeah. So in a way you are labeling that way. Yes, that sounds good. Yeah, you can do 4 by 4 by 2. Yeah, that would be fine. Yeah, if you know which action you're executing, which state you're in, and where is the goal position, you can use that. Yeah. Exactly. Yes.
So we need to formally formally define the entity in the code, right?
Yes.
And the states involved like the position as
orientation. Yes. Yeah.
Because if normally we use this per step we see it as a vector, right, of a certain dimensions. The real number to the certain number of dimensions. But the positions they are tuple.
Yeah, discrete. Right.
It's kind of it's kind of something it's not very creative to flatten all the tuples and put them in a vector.
Yeah, you don't have to. You can leave them like I did here.
Can I just use tuple as an element in the vector?
Yes, you can. Yeah. What I did essentially here is fine. So I said P is 0, 0, 1, 0, 0, 1, 1, 1, something like that. So I would say if you explain in the report the state space in this way, that's what we mean by defining the entity.
Actually, the door position will be a variable type because there's a continuous door.
Yes. But yeah, that's what I mean. That's what we mean by defining the MP. You need to define these elements here. What is the state? What is the control? What is the planning horizon? What's the stage cost? What's the goal cost? Obviously, it's hard in the report to give the exact definition. It's it here for the motion model. It's sort of that correct for bounds. But you want to explain at least how it's defined. Okay. More questions? Yeah.
Yeah, so even though we were told to use the dynamic programming, but wouldn't Shortest Path be a more sort of suitable approach to the question?
No.
I mean,
it can, yes, okay, it can, okay, if you run, so we saw that for deterministic problems, which this is, they're equivalent. So you can formulate a shortest path problem, which you can solve with Dijkstra or A star, give you the exact same solution, but you're not allowed to use it per environment. If you run a single search that gives you a policy, and you use that, I accept that solution. I'm not allowing it because it's more complicated. We haven't discussed how to do that, or like the A star or Dijkstra algorithm we discussed. It doesn't give you a policy in the end. So what is the policy? So I want you to store the policy for all possible environments and then use it. So yes, technically you can.
The
But
shortest path, the sort of the edge I'm taking from every node on the shortest path, wouldn't that be the policy?
let's say again.
Sort of say I have already found the shortest path.
Yeah.
And then for every state on that path, I know the next edge, and that edge corresponding to the sort of the control input I'm going to be.
Yeah, it is. Yeah, you can extract it, but it's tricky. You need to compute the shortest path to multiple starts because you don't know which of them will be the true one. So there are 36 possible initial starts. So you need to make sure that all of those were in the open list and you computed the cost to those. So it's like multi-start to one goal, and then you need to record the possible actions for all these. So yes, it can be done, but it's not straightforward. Or I mean, it's not hard, but it's more than what we've discussed in the lecture. While the dynamic programming algorithm is there on the slide, so you could just implement it.
Okay. Understood.
Yes, but we don't want things like if the door is open, follow this path. If the door is closed, follow this.
But it's like going to be, if door is open or not, it's going to be a part of the input. And then I use that input to look up a table or something, and then
Yes,
sort of determine the
exactly.
policy.
Yes, whether the door is open or not is part of your state. And you use your state to look up your policy.
Exactly.
Yeah.
So, I also want to sort of discuss the reduction between the tourist pass and the
Optimal control.
optimal
Yeah.
control, yeah. So like from one direction, I think the size doesn't change, there's still ON. On the other direction.
Number of states, yeah.
Yeah, on the side, like sort of,
We introduced a dummy goal, yeah.
yeah, so sort of will make that N squared. Is that the case?
Yes, true.
Is there better sort of like, better boundaries for that?
Yeah, you can probably do better than this, but we just showed that there is a way to convert them and they're equivalent.
But not in the runtime, like in the runtime, they're not equivalent.
Correct, yeah, but we don't actually run the algorithms this way, so this construction was just to show that the algorithms are equivalent, but we don't, in practice, we never actually did this construction, right? I didn't tell you, if you have a shortest path problem, build this N squared state space and then run the dynamic programming. We defined the dynamic programming algorithm directly for shortest path. Yes, so there is a better way, but it's not necessary. We just need to show that there is a way, yeah.
Okay, understood.
Yes, there probably is a way to do it with fewer states. That's true, but the algorithm in the end, he didn't use that construction.
Okay, understood, thanks.
Okay, any more questions?
Wait, can we do the next step?
Yeah.
Yeah, thank you. Sorry, guys. Trying to get it.
So maybe let's do the next step.
Yeah, thank you.
And stop here. Let's see where we're. Yeah, so next step is, well, we have the Q function. We said to compute it, we need to do it for every X and every U, and we do this with L and F, which we defined on the previous slide. And then we just need V6 of X is going to be the min over U of QXU, right? So if Q is a matrix, you just take min along the second or the first dimension if we label from 0. And we set that to be V6. At this point, you can throw away. Well, you want to check if V6 and V7 are equal. So we can say if V6x equals V7x for all x, stop. Otherwise, you can compute pi 6. Well, maybe pi 6 would have been better earlier. Sorry. Yes, pi 6. Sorry. Pi 6 is the same, but the argmin, right? Pi 6 of x is, and I'm writing equality here because we could. And then if V6 is equal to V7 for all x, then stop. And that's it. Then you would repeat.
Okay.
So I think that.
I don't know if I'm mistaken on this, but like I did kind of similar by hand, like I computed the Q function and everything. What you get in the end is the positions of like the sequence of states that you hit, but I don't get how that translates to like a control policy, like, because you're gonna get the coordinates that you hit along the way, but like how do you know that I didn't turn right here and go down?
Oh, but so
Is
this
it-
pi thing will give you the control. So the argument is the u which achieves the minimum. So you would save that. So no, at this state I need to use this control.
Okay, so that does give you it back, yeah. But like, in order to get those turn rights and turn lefts, because like this makes sense for if you're moving in like a grid motion, but if you turn right, like do we just have to include that in the original state
Yes.
representation and then everything takes care of itself?
Yes.
Okay.
Exactly.
Okay. Gotcha. Okay, that makes sense.
Okay, I can do the last question. I need to go. Anyone has a burning question? Yes, go for it.
After we find out the optimal control for every time step, for every state, how do we eventually find the optimal control for this solution?
This pi is the optimal control.
Yes, but it's for every state.
Yes, whichever state you're in, you call pi, and this gives you the control.
Yeah, but we eventually need to have something like this one state. Have some lines. So how do we turn that into something?
Well, in the actual environment you get, you'll have some initial state where you are, where the key is, where the goal is, where the door is. This will be your initial state at time 0. So you call pi 0 of your initial state, this will give you the first action. you record it in, so this will be the first entry here. Then you use your motion model to go to the next state. And you apply one at that new state. This will give you the second goal. You record it there, and you keep going until you reach the goal.
So the data we are in the high 1 to high 7, it's in the form of this byte.
Correct, yeah, those are the controls, yes. Yeah, exactly.
And then, okay, before we define control, it's something, it was something like this. At the beginning, we defined
Damn. That's tough, man. It's tough.